be discussing a little bit about molecular dynamics modeling of materials. So I guess most of you, from what I talked with Professor Mondal, that most of you have a background of civil engineering. And this topic called molecular dynamics is something which is not typically taught at civil engineering curriculum within our country. So I'll start with something very basics, something which you all are familiar with, and then slowly we will go on to add complications. So in this first lecture, I want to devote mostly to why one should go for molecular dynamics based modeling of any material. That is, why should we go for any kind of atomistic modeling? So to present this case, by the way, please feel free to interrupt me if you do not follow any part. Since we are doing it in an online mode, it is very difficult for me to gauge how much you are able to grasp. I try my level best, but please feel free to interrupt me. So, as civil engineers, we typically deal with very, very large scale systems. So, on the figure which you see on the right hand side, you have on the left hand side, you have aeroplane, you have gas turbine, you have ship structures, and likewise you will have, especially when it comes to our civil engineering structures such as bridges or buildings, they typically form what are known as macroscopic structures. Macroscopic in the sense their length scale spans from a few centimeter to at least a few hundreds of meters. So as you can imagine, a large ship will have a length of around 400 meters and so forth. An aeroplane could have, a Boeing or a Airbus plane could have a length of around 100 to 200 meters. And all of these fall under the scale of macroscopic systems. Now, these macroscopic systems are typically governed by continuum mechanics. And this we will deal in a little while in more details in the figure in the right hand side. Now, the properties of interest for any such large scale structure, that is the property that we as engineers or researchers are interested in, are typically manifest at that, but their origin can be traced back to much sooner. For example, if you see very carefully in either of the three cases which I have demonstrated over here, the aeroplane, the gas turbine, or the ship structure, the major problem that we tend to look into in such structures is related to fracture. We try to understand how and if there would be any fracture within the system. So fracture as in, would there be any cracks? Would the cracks propagate? And so on and so forth. How quickly the crack will propagate, whether they will be leading to catastrophic failure or not. So all of these things are typically of interest to us when we talk about large-scale structure. And this is also true even for our civil engineering structures such as buildings and bridges. You must have seen at least a very recent video of a bridge collapsing due to a ship impact in the United States, called Baltimore, right? So these fracture, although it manifests at macroscopic scale, it can trace its origin back to much smaller microscopic scale. That is because fractures typically occur in a system when the bond between the different kinds of atoms start to break. So if you zoom in very carefully in any material, you would find that this material, although may seem like this material, they are typically made up of a large number of what are known as crystals. Crystals having different orientation. And these crystals are typically a group of such crystals come together to form a grain and a grain boundary. Cracks typically propagate through this grain boundary. Hello.
Yes, yes. It's
So
audible.
I think someone muted me. Ah.
Oh,
So,
sorry.
so what I yeah. So typically these cracks proceed by because of this grain boundaries being separated, and these grain boundaries are nothing but weak links between the different atoms. Now, if you zoom in even more, you would hit the domain where you can actually see individual atoms and molecules within the system. So to sum it up, what is happening is, even though we are trying to study a process such as fracture at continuum mechanical level, at large scale system level, but the entire process starts because of the breakage of bonds, because of the loosening of the bonds at atomic scale. So this should give you the first reason why you should study atomistic, or why you should go for atomistic modeling of different kinds of materials. If you want to understand the property of a system, different kinds of properties of a system, the first thing that you have to, or the best approach to study such a system, would be to go for atomistic modeling. Now on the right hand side, any questions from this, why we should go for atomistic modeling? Please feel free to ask if you have any questions. Okay. So on the right hand side, you see the different domains of continuum mechanics, which in more general can be clubbed as classical mechanics. Depending upon whether we have a non-zero value of compressibility, that is the bulk modulus, and the shear strength, or the shear modulus and viscosity, we end up with different kinds of formulations of continuum or classical mechanics. For example, when bulk modulus is infinity and the shear strength is almost equal to zero, we end up with hydrostatics. When the shear modulus is finite and the bulk modulus is finite, we end up with what is known as solid mechanics. Where when we have a finite value of bulk modulus but a zero value of shear modulus exactly equal to zero, we have gas dynamics. When we have, likewise, when we have the finite value of bulk modulus and a finite value of shear modulus, but also have acceleration into the picture, that is non-zero acceleration, we end up with what is known as structural dynamics. Likewise, for non-zero acceleration, but k almost reaching infinity, that is the bulk modulus reaching infinity, but the shear modulus becoming equal to zero, we have inviscid or inviscid fluid dynamics. When the shear modulus also becomes finite now, greater than zero, but less than infinity, that is, it's a finite quantity, we end up with fluid dynamics if we have acceleration in the picture. Similarly, if our shear strength is, or shear modulus becomes infinity, bulk modulus becomes infinity, and we have non-zero acceleration, we have what is known as rigid body dynamics. So as you can see, depending upon the assumption that we are making on the material property, our formulation of continuum mechanics changes. For example, and that depends upon the situation, that depends upon the problem that we are trying to study, for which we have to go for appropriate modeling technique. So at atomistic scale, as I will show you in a short while, the method is powerful, and the method is extremely powerful. Not only that, the basic formulation remains the same, irrespective of whether you are working whether you are working with a gaseous material or a liquid material or a solid material. So this commonality is typically absent in continuum mechanics. So as I was telling you, for continuum mechanics, typically we work with large size systems starting from a few centimeters, millimeters to hundreds of meters. Classic examples which we have just discussed. And the characteristics time scale of interest is from a few microsecond onwards. So we start to simulate the processes, and we try to understand the processes from a few microsecond onwards. For example, let's say there is a crack which is propagating within a material. So, and there is a catastrophic failure that the material will undergo. It will undergo in a few microseconds. Okay. On the other hand, the next scale of, if we go down one scale where we are looking into a few grains together, we are working with what is known as microscale mechanics. Here, the size is of the order of few micrometers, that is 10 to the power minus 6 meters. And characteristic time scale, that is the time scale of interest, the processes which occur at this microscopic scale start from a few nanoseconds and continue until a few microseconds. When it comes to nanoscale mechanics, which is the focus of atomistic modeling, we can go we can go up to a few hundreds of nanometers. and the characteristics timescale is only a few hundred nanoseconds. Now, this creates a problem because that creates a huge bottleneck when it comes to atomistic modeling. For example, the largest system that I have seen that can be solved, that has been solved on a computer related to atomistic modeling is a system comprising a trillion atom. A trillion atom is nothing but 10 to the power 12, I believe. So, and even a mole of a substance comprises 10 to the power 23 atoms. So, the largest system that we have solved so far, and just to give you an idea, that system took one entire full month on a supercomputer to run continuously. So that system is also at least 10 to the power minus 11 times smaller than what even a single mole is. And just to give you an idea about how small a nanosecond is, well, all of you are familiar with what a second is. So typically, the smallest of the motions, the vibrations of the sum of the bonds occur in the scale of few picoseconds, that is 10 to the power minus 12 seconds. So it's only a few thousand, 10,000 times greater than a few picoseconds. Now, the interesting part is continuum mechanics, be it or microscale mechanics or nanoscale mechanics, each of them are going to solve a completely different evolution equation. And this is one of the reasons that's because of which we need different mechanics at different length scales. To give you an idea, so the continuum mechanics is typically based on continuum solid mechanics is typically based on the three conservation laws. The first equation which you see over here is the mass current conservation equation. The second is the momentum conservation equation. The third is the energy conservation equation. Here rho represents the density, t is the time, v beta represents the velocity in the direction beta, x beta represents the position along the beta direction. Sigma alpha beta is nothing but the stress component alpha beta, and E is the specific energy of the system. So the basic assumption while we developed these three equations is that no matter how much you zoom in, you take a material, you keep zooming in, you keep zooming in, you keep zooming in, at any point in space, matter is always going to be present. So I repeat once again, the basic assumption of continuum mechanics is no matter how much you zoom in, there is always a material present, or a mass or a matter is present at a material point in space. What this gives us is that it enables us to define what are known as vector fields, such as the density of particle of the system as a function of x, the stress field within the material, so on and so forth. And a consequence of this assumption is that there is no void space which is present within the material. Another consequence is that we can develop what are known as representative volume elements for such continuum mechanical systems. So, but this assumption, one of the consequences of this assumption, as I was telling you, is that no matter how much I zoom in, there is still always going to be a matter present at a material point. This assumption starts to fail if we keep zooming in, keep zooming in, keep zooming in, and hit the level of a atom. And as I will show you in some next few slides, that in reality the empty space covers up the most of the region within a single material crystal. Apart from this, there are other reasons why we cannot really go for the same kind of solution techniques that we adopt for continuum mechanics for atomistic scale mechanics. That is because, as I was just telling you, the nature of material, the true nature of material is discrete. It's not continuous. Not only that, because of this, we at atomic scales, we have to deal with millions of degrees of freedom. For example, if I assume that a point, an atom is basically a point mass, then what it will have is every atom will have is 3 degrees of freedom X, Y, and Z, and multiply that with the number of atoms within a system that you are studying. So, for example, if you have n degrees of freedom, n atoms within the system, you will have 3n configurational degrees of freedom within that system. Uh, so the consequence of having such millions of degrees of freedom within the system is actually a bottleneck, in the sense that we cannot go for simulating very, very large systems. Okay. So another way in which the atomistic scale mechanics is different from continuum scale mechanics is because of the what are known as the non-local effects. So typically when we have continuum mechanical models, unless you work with non-local theory, we do not take into account the non-local effects which arise within the matter. Non-local effect means that the material at a continuum level is only going to be affected because of its surroundings. It is not going to be affected by whatever is happening far away from its surroundings. On the other hand, at atomistic scales, we have non-local effects within the picture. That's because of the what are known as long-range potentials, a classic example of which is the Coulomb's law, Coulomb's force field. So electrostatic force field or Coulomb force field scales down, as I will show you in a short while. It scales down as 1 by r, not 1 by r square, not 1 by r cube, but it scales down as 1 by r. As a result of that, what is going to happen is that it's a very long-ranged force field, and charge on one atom is going to influence the dynamics of a far away located atom as well. The third reason for the difference in continuum and atomistic scale mechanics arise because of what are known as non-equilibrium transitions. So this is a slightly advanced topic. So because of the shortage of time, I will not go in more details. And perhaps the next one is relatively easier to understand, and that I will stress in more details in a short while. So at atomistic scale levels, what is happening is surface stresses, surface energy, and if I combine all of them in terms of surface and call them surface effects, they start to play a major role within the dynamics. At continuum scale level, we do not really take into account the surface effects that much because they do not feature in that importantly, and the reason we will see in the next few slides. Apart from that, there are other issues which may arise. For example, there could be thermal effects and vibrations. This is a major important concept at atomistic scale modeling. So anything that you are simulating at a non-zero temperature, that is non-zero Kelvin temperature, anything that you are simulating using atomistic scale modeling, you are bound to have some kind of thermal vibrations. This is because temperature goes hand in hand with the kinetic energy of the atoms present within the system that you are trying to solve. As a result of that, the atoms tend to move around. So let's say I want to focus on a material like steel. At continuum scale level, we do not really take into account the vibration of individual atoms. But at atomistic scale level, these vibration of individual atoms, because of non-zero Kelvin temperature, plays a major role. There could be random defects within the material, which we tend to typically discount at the continuum scale level. And these defects play a significant and an extremely important role when it comes to atomic scale dynamics. So just to give you an idea, I am sure all of you have heard about the material known as graphene. So graphene is a material which is known to have the largest thermal conductivity. So it has a thermal conductivity of the range of 3000 watt per Kelvin per meter square. So that kind of high thermal conductivity you have for pristine graphene. Pristine graphene as in graphene sheet without any defects. The moment you start introducing defects in graphene, its thermal conductivity falls significantly smaller than the estimated one of 3000. At atomistic scale level, fluctuations become important and they start to dominate over the mean. And just as a consequence of that, what is happening is that the second law of thermodynamics, which is one of the most profound laws that have been proposed in the scientific literature, it's applicable from quantum mechanics to atomistic scale mechanics to continuum mechanics to astronomical level problems. But since fluctuations start to dominate over the mean at atomistic scale level, the usual interpretation of second law is needs to be modified, and now it takes a probabilistic form instead of being the deterministic form. So although it is beyond the scope of this lecture, you can take a look if you are interested in what is known as fluctuation theorem. And just to give you an idea, what it says is the smaller the system that you are trying to simulate, and the shorter the time that you are trying to investigate. In such cases, there is a finite probability of heat to flow from a colder region to a hotter region spontaneously. On the other hand, being probabilistic in nature, if you increase the time of your analysis, or if you increase your system size, that is, you reach the continuum limit, you revert back the classical continuum mechanical description of the second law of thermodynamics. One last reason why continuum mechanical theories cannot be directly used for atomistic scale mechanics, well, there are situations which are only observed at atomistic scale level, they never are really observed in continuum mechanical level. And one classic example of that is ballistic thermal transport. What do we mean by ballistic thermal transport? Well, it means that the thermal conductivity increases linearly as your system size increases. Now, this can have a profound consequence for us engineers, for us, especially the civil engineers. Imagine you are designing some kind of a building where thermal conductivity, if not increases, but let's say decreases monotonically as your system size increases. You can come up with a material, you can come up with a design which would lead to an insulated building by using such kind of a material. But this phenomena is typically not observed at continuum scale level. I'm once again reiterating, and it is only observed at atomic scale level. So now let me show you over the next few slides the amount of empty spaces that you typically get. So in this slide, you see over here a material known as high entropy alloy. So high entropy alloy is basically it's an up and incoming material. The material that we have chosen is what is known as the Cantor alloy, and it comprises of 5 different elements. The first figure on the left you see is the actual atomistic simulation which we had conducted for our high entropy alloy work, which I think a couple of years ago got published as well. Now the different colors indicate the different kinds of atom. Now let us say from this figure I just simply deleted three of the 5 elements, so that only 2 of the 5 elements now remain. So you can see this in these 2 elements in this middle figure. Next, I only chose one of the 2 elements and I created this figure on the right hand side. The system size that you are seeing over here, the X direction corresponds to 105.72 nanometers. The Y and the Z directions are the same. They correspond to 21.144 nanometers. So we are dealing with a system which is of nanometer in size. Now, as I keep deleting the atoms from this 5 element based high entropy alloy, you can see that the white space within the domain keeps on increasing. Here you see there are more white spaces than here, and here also you can see there are more white spaces than in this case. So the reason for me to show this slide is simply to emphasize that if you keep zooming in inside a material, you will end up with a large amount of void spaces. And because of this presence of such void spaces, the basic assumption of continuum mechanics, which we just discussed, based on which we were able to define the fields, we were able to define not just the stress field, but also quantities like displacement field, deformation gradient, and so on and so forth. Because of the presence of these voids, the entire concept of field now gets to be kept aside. Another important thing is in the previous slide, I told you that each particle comprises three configurational degrees of freedom. But when it comes to atomistic dynamics, we not only deal, since every atom, every particle, every atom, every molecule has a vibration associated with it at non-zero temperature, we don't only have the three configurational degrees of freedom, we also have three momentum degrees of freedom. So in essence, there are a total of 6 degrees of freedom per atom, and therefore you will end up with 6 n-dimensional 6 n degrees of freedom overall if you have n atoms within the system. Uh, to the figure on the right hand side of the last slide, I kept zooming in again and again, and I then ended up with a figure which is shown over here on the left hand side. What you can see is, you can clearly observe is the void spaces. In presence of so much of void spaces, we are going to typically have certain consequences, which we will discuss in the next few slides. On the right hand side, I have a relatively small system of an ordered lattice, and in this system also you can see how much of void spaces are. Now, please note that in order for visualization purpose, I have zoomed in the size of each individual blue particle over here. Typically, they are point mass, so they will occupy just a single point in the XYZ coordinate system. Okay. So now let us focus our attention on the surface effects. So consider this right hand side figure of this slide, and imagine that we are making an imaginary cut shown over here in this red colored in this red region. And we extend this cut only up to a short distance. Now, for the surface to remain in equilibrium without any additional stresses in the volume of the crystal, we have to apply external forces onto the atoms near the surface of the cut. And these forces must be equal and opposite in nature on the two sides of the cut face. After that, we measure what is the total force per unit length of cut, and that we call it as the surface stress, which exists across the line of the cut. Now, the smaller the system, the more is the surface effect. Why such is the case? Well, you can imagine, let us say you have a cubical system of n by n by n particles. So in essence, you have n cube number of particles. Now in this cube, there are 6 faces, and on each face you would have n square number of particles. So overall, the number of atoms present on the surface is 6n square, and the number of atoms present in the entire bulk, in the entire volume, is n cube. So as you can see, that the area to the volume ratio decreases as 1 by n. And as n tends to infinity, the surface effect decreases. This is the precise reason at continuum mechanics level, where n is approximated as infinity, the surface effects do not play any major role in comparison to the atomic scale dynamics. So just to give you an idea, what happens, what is the effect of the surface stresses? We have over here the same system, and we are taking now the cuts at different levels. And you can see this on the figures on the right hand side are nothing but the potential energy distribution of the potential energy at different domain. As you can see that as we keep on going more and more towards the boundaries, we have a higher potential energy than what is present within the bulk of the system. And this system is a very small system. It has only 160 atoms of iron, and it has been simulated using what is known as EAM potential. For those who are interested, I can recommend a book which details in much more depth what the different kinds of potentials are. But the crux that I want you to take from this slide is that the potential energy changes as one approaches towards any of the surfaces. Uh, okay. Now let us focus a little bit on the non-local nature. So, which is again not present so much in continuum mechanics, which we tend to typically do not take into account. Now, when it comes to atomistic modeling, as I was telling you, that any atom or molecule and ion often carry charges. Charges as in they could either be positively charged or they could be negatively charged. We know from the basic Coulomb's law that two particles having charges Q1 and Q2 will interact through a electrostatic potential which is proportional to 1 by R. The nature of this potential, the denominator has a value of R. It is a very slowly decaying potential. The consequence of this slowly decaying potential is that the interaction between two atoms can occur beyond the immediate neighborhood. In other words, two particles present far away can influence each other. In fact, there are what are known as the non-bonded interactions present within atomistic scale simulation. Non-bonded interactions are nothing but, well, you can imagine that you have a bond. A bond will have its own interaction between two atoms, but two atoms can also interact not through by means of any bonds, but through other means. So they are known as non-bonded interaction. And one such non-bonded interaction is the Coulomb's law. So what you will get is, unlike at the continuum scale, there is a spatial correlation in the property of material at a point with the property beyond its immediate neighborhood. And this is a major reason why continuum mechanics and atomistic scale mechanics are significantly different. So just to give you an idea how much the how much the Coulombic force, how does it change over distance? So as x approaches 0, the magnitude of the Coulomb force, which varies as 1 by r square, approaches almost infinity. Okay, it is infinite. It has short, or rather it has a long tail, and you can see that at a distance of almost 4 units, the value is not 0, but it is actually equal to 0.25 units in terms of force. At a distance of 20 units between the two, when the distance is 20 units between the two particles, the force is still not small enough to be negligible, and it takes up a value of 0.05. So this is how the slow decaying Coulombic force looks like, and this causes the non-local effect within our atomistic scale system. I'll leave out the non-equilibrium transitions because of the shortage of time, but I want to invest some time into telling you about the thermal effect once again. So as I was telling you, temperature remains coupled with velocities of the particles at atomistic scale, because of which there is spontaneous motion of the particles at any non-zero value of temperature. In fact, using molecular dynamics, you cannot run any dynamical simulation at 0 Kelvin because atoms are bound to move. And if they move, they are going to have kinetic energy. And if they have kinetic energy, they will have some finite temperature of the system. You cannot simulate any dynamics at 0 Kelvin using molecular dynamics simulation. Unfortunately, I have prepared a video, but this video is not playing. So I wanted to demonstrate before you how how an atomistic scale simulation looks like. But nevertheless, I do have certain slides, which actual videos that I will show you in a short period of time. So Another reason why we should go for molecular dynamics is the changing landscape of engineering. And this perhaps is one of my favorite slides. And this is most relevant to us civil engineers because civil engineering as a profession has historically been based on hit and trial methods. For example, these days you can see what are known as nanosilica infused concrete. So researchers have come up with such nanosilica infused concrete, and they have observed that such concrete has the good amount of strength over the normal OPC based concrete. But what is the right proportion of using the nanosilica? This we civil engineers typically know by performing large number of experiments at laboratory scale. Using atomistic scale dynamics, well, you can actually simulate the stuff and you can find out what is the right quantity, and then you can go to the lab and perform experiments. Okay. But one thing is to be certain, one thing I need to emphasize again and again, this atomistic mechanics and molecular dynamic simulations, they are typically performed on computers. In other words, we are going to integrate some kind of equations to obtain the trajectory of the system. The trajectory of the system as in the position and the velocity of all the particles at different time shots. The reason we have to perform it only using on using computers is because we as researchers, at least I as a researcher, do not even possess the ability of analytically solving a system comprising of three particles located at the vertex of an equilateral triangle and evolving under a central potential, that is evolving under a gravitational potential. So if I change the position, I'm not sure whether this slide the figure is visible properly. Let me zoom in, perhaps then it will be clear. So what is happening is I have three particles, one initialized at this position, one initialized here, and one initialized here. And I let them evolve under the central law, that is the gravitational force. First case, I am starting them from the exact vertex. And in the second case, I have just deviated one of the particles by a very, very small amount from one of the vertex. Now, as you can see, the dynamics in the two cases are completely different. So when the initial position of these particles are perfectly on the vertex of the equilateral triangle, that problem can be solved analytically, and that is shown over here in red color. The moment I change the vertex of one of the particles by even the smallest amount, you can see these black lines correspond to that new trajectory, and you can see that they are not very, very similar to what is there for the red line. So imagine now evolving this system for hundreds of thousands of such time steps, and you will observe a large deviation in the trajectory. So the reason I'm telling this to you is simply because if we cannot even solve this such simple three-body problem because of the small change in the initial condition, we do not possess any analytical ability to simulate a large-scale problem of the kind that I was showing you in the previous slides, such as the high entropy alloy system. But these computer simulations have an issue. The issue is they take a long time for the results to come. I'll tell you how much time it usually takes in the next lecture. But the advantage is the method of molecular dynamics is essentially exact, and there is no assumptions involved so long as the force field is chosen correctly. Where does the force field come into the picture? That we will see in a short while. So what is the power of molecular dynamics? Well, the power is limited. I mean, it's based on your imagination. You can solve a system of a few hundred particles, or you can solve a system comprising a trillion of particles for answering several interesting questions. So these three problems that I have shown over here are typically encountered in solid mechanics, both at continuum level as well as at atomistic scale level. We have a crack propagation in a pre-notched plate. We have two elastic rubber rings colliding. We have a cantilever beam which is subjected to a tip impact load. These three problems can be solved using both continuum mechanical methods as well as atomistic scale methods. The choice is yours as to how complicated you want to go when it comes to atomistic scale method, whether you want to discretize this problem in a few thousands of particles or you want to go for a few billions of particles. Another important domain where molecular dynamics is used is for the computational discovery of new materials. There are several different new materials whose existence has first been shown using molecular dynamics and then it has gone on to be synthesized in the laboratory scale. You can also understand the working of several nanoscale devices such as nanoscale switches, nanoscale motors. Not only that, you can come up with very, very interesting cases which you cannot explore with the continuum mechanics framework. For example, the evolution of the dislocation within a material as plasticity occurs within that material or as failure occurs within a material. So you can see that the system on the left hand side is a billion atom system. It has been taken from the work by Abraham et al., which got published in PNAS in 2002. And it's just a 20-year-old work. This billion atom system also took more than a month on its then fastest supercomputer. So you can refer to this paper and it's a very interesting paper. Lastly, I want to detail what all applications you can do with molecular dynamics. You can find out the properties of interesting materials such as graphene or carbon nanotube. The graphene is shown over here on the left hand side. The carbon nanotube is shown over here in the middle, or rather the boron nitride nanotube is shown over here in the middle. And there is a new kind of a material, naturally available material called fluoroapatite, which is shown over here in the right hand side. You can use molecular dynamic simulation to explore and understand their mechanical properties, their thermal properties, their electrical properties, and so on and so forth. You can investigate problems such as what is the behavior of material going to be under loading, that is the ductility and the fracture behavior. You can investigate thermal transport phenomena, that is calculate thermal conductivity, coefficient of thermal expansion, heat capacity. You can find out what is the effect of impurities and imperfections and grain boundaries on the mechanical behavior. You can understand the role of doping as to how doping a material with the different material changes the property of the host material. You can create some very, very interesting new situation for studying different kinds of problem. One of them is the differential thermal conduction problem, which I studied long time back during my PhD days. Last slide, which I want to show in this domain is the computational discovery of materials. So you can see over here, what are known as the single layer 3-5 materials, and all the existence of these two-dimensional materials have been proposed using molecular dynamics. There is a new zeolite-like material. Zeolite is typically used for water purification. They have been developed using molecular dynamics first, and then later on it was developed at the laboratory stage. Subsequent to that, we can also observe plant-based inhibitors, which is typically used in the chemical engineering domain. Not only that, since we have just recently come up from the COVID pandemic, come out of that, molecular dynamics simulation, I just want to emphasize that it can also be used to simulate the full virus itself. In fact, it has been used already to simulate influenza A virus and satellite tobacco mosaic virus, which is shown over here. And I think I remember reading an article where it was showing that where it dealt with that molecular dynamics can be used to simulate COVID virus as well. So with this, I'll stop the first lecture. If you have any questions, feel free to ask. Otherwise, we can move over to the next one.